A lot of our listeners, they're really into philosophy, like digging deep into those big, complicated ideas, but without getting bogged down in all the technical jargon.
Right.
So today, we're doing just that. It's going to be a deep dive into the work of this major mathematician. His ideas, they still have a huge impact on philosophy.
Yeah. We're talking about Richard Dedekind. He was a giant in 19th century math, born in 1831. You might know him for things like algebraic numbers or his theory of ideals, which was revolutionary.
Right.
But today we're focusing on his more foundational writings, the stuff that'll really resonate with the philosopher in you.
Exactly. We're diving into his works like Continuity and Irrational Numbers from 1872, and then The Nature and Meaning of Numbers, which came out in 1888. And what makes Dedekind so fascinating, especially with those who love philosophy, is how closely his actual mathematical work is tied to these deep questions about what math really is, like the nature of math itself. Trust me, his ideas continue to have a huge impact on the philosophy of mathematics today.
Absolutely. To really get the full impact of Dedekind's work, though, you need that historical context.
Right.
The 19th century was all about making analysis super rigorous and based on arithmetic. Basically, before that, the way we thought about smooth, continuous stuff like curves and motion, the things calculus is all about, really relied a lot on our visual intuition of geometry.
Yeah.
But the arithmetization movement, with Dedekind as a key player, wanted to rebuild all that on the more solid ground of numbers and their properties. Not relying on geometry because sometimes those pictures can be misleading.
Okay.
Part of this push came from those ancient Greek discoveries, like how the diagonal of a square can't be expressed as a simple ratio of its side. It really messed with the idea that you could express all magnitudes as simple ratios.
Yeah.
And then calculus itself had its own issues, especially in the early days when it relied on those infinitesimally small quantities.
So let me see if I'm following you. For a long time, numbers felt like they were separate from things like lengths and areas. Numbers, you count them. Lengths, areas, those feel continuous.
Exactly.
And those Greek discoveries, like that square root of 2, they kept those two worlds kind of apart. That's a philosophical challenge in itself. Then you have algebra and calculus coming along, and suddenly you need this unified way to talk about both.
Right.
And Dedekind's work steps right into that gap, aiming to create this unification, but using the logic of numbers themselves. He doesn't rely on geometric intuition or just what feels right.
Exactly. And that brings us to the whole point of our deep dive today, especially for you, our philosophy-minded listener.
Yeah.
We're going to break down Dedekind's approach to the foundations of mathematics, trying to make his ideas about continuity, the nature of numbers, and the logical structure of math really clear.
Right.
And of course, we're going to highlight how crucial his work is for philosophical thought, for how we understand what mathematical reality even is.
Okay, let's jump right in then. His book, Continuity and Irrational Numbers, the one from 1872, it tackles the foundations of analysis head-on. What was the main problem he was trying to solve there, especially from a philosophical perspective?
The core issue for Dedekind was this. How do you create a super rigorous arithmetic foundation for the real numbers, but without relying on geometric intuition, which can be shaky?
Okay.
And by real numbers, I mean both the rational numbers, those are your fractions, and the irrational numbers, things like the square root of 2 or pi.
Right.
And what's interesting is that his motivation wasn't purely theoretical. He was teaching calculus in Zurich at the time, and he felt he needed this more solid, logical basis for the concepts he was teaching.
Yeah.
That focus on clarity for teaching, that's something philosophers can appreciate, right?
Absolutely.
Yeah.
Absolutely. And in this search for a solid foundation, he came up with this idea of cuts, right? For someone trying to grasp this for the first time, how would you explain a Dedekind cut?
Okay. Imagine you're slicing through the number line of rational numbers, like with a knife.
Okay.
You're dividing them into a lower set, we'll call it A, and an upper set, B. Now, a Dedekind cut has 3 very specific rules. First, every single rational number has to go into either A or B. No straddling the fence.
Okay.
Second, every number in A has to be strictly smaller than every number in B. So you're keeping that natural order.
Got it.
And third, set A, the lower one, can't have a biggest element. Like, no matter how large a number you find in A, you can always find an even slightly bigger one that's still in A.
So it's like you're making this precise cut through the rationals. But where does the philosophical part come in?
The philosophy kicks in when you realize that some of these cuts, they don't land right on a rational number. It's like there's a gap there.
Okay.
So think about this cut. Set A has all the rationals, call them x, where x squared is less than 2,
Hmm.
and set B has all the x's where x squared is bigger than 2. Now, the ancient Greeks, they figured out there's no rational number that you can square to get exactly 2. So this cut, it splits the rationals perfectly, keeps the order, and A doesn't have a biggest number. You can always find a bigger one whose square is still less than 2.
Yeah.
But there's no rational number sitting right at that cut.
Right, right.
For Dedekind, this was a big deal. It showed him that there's this fundamental incompleteness in the rational numbers themselves. There are gaps. And these cuts, they reveal those gaps.
So by using this tool of cuts, and it's defined entirely within the world of rationals, he exposes a limitation of that very world.
Yeah.
And this is connected to a structuralist approach, right? What's the philosophical importance of that here?
Exactly. Dedekind wasn't just thinking about individual rational numbers.
Right.
He was looking at the whole system of rational numbers as this unified thing, this actually infinite set that's a complete mathematical object in itself.
Okay.
Philosophically, this is a big shift. Instead of focusing on what individual mathematical things are, he's trying to understand them through their relationships within a larger structure. He saw the rationals as this linearly ordered set where you can add and multiply, and everything stays within that set. Today, we call that an ordered field. This emphasis on the overall structure, not just the individual parts, is a hallmark of mathematical structuralism, and it has huge implications for how we think about mathematical existence and truth.
Okay, so he's found these gaps in the rationals using these cuts. How does he then fill those gaps and actually construct the real numbers? And how should a philosopher interpret this creation?
This is where Dedekind gets super clever and where the philosophy gets really interesting. So for every single possible cut on the rationals, whether it lands on a rational number or shows one of these gaps, Dedekind basically creates a new mathematical object.
Okay.
He calls it the real number determined by that cut. So for the cut representing the gap where the square root of 2 should be, he creates the real number square root of 2. And for a cut that lands on a rational number like 1.5, he creates the real number 1.5. All these newly created real numbers, along with very precise rules for how they're ordered and how you do arithmetic with them, all coming from the properties of the cuts, they form a brand new, more complete number system, the real numbers.
So philosophically, this raises all sorts of questions about what mathematical creation even means. Are these real numbers something we discover or something we construct through these definitions? Dedekind seems to be leaning towards this idea that we construct them.
Exactly. And this new system has some crucial properties that get right to the heart of the philosophical issues of continuity. First, all the rational numbers are perfectly embedded within it. So every rational number has a matching real number, and all the order in arithmetic works the same way.
Okay.
But even more importantly, this new system is continuous, what we call line complete.
Okay.
This means that every single Dedekind cut you make on the real numbers themselves will actually correspond to a real number. There are no more gaps. This finally gave us a unified way to define both rational and irrational numbers. They're all simply elements within this continuous system of real numbers, defined by where they sit on this continuous line.
So he reconciled the discrete and the continuous in this really elegant way. Now, you mentioned earlier that Cantor also found a way to construct the real numbers using Cauchy sequences. How is Dedekind's approach different, and why do you say his gives us a clearer philosophical understanding of continuity?
That's an important difference for the philosopher. So Cantor, he looked at these infinite sequences of rational numbers that get closer and closer together. We call them Cauchy sequences.
Okay.
He then defined real numbers as these sets of equivalent sequences. Now, both constructions work mathematically. They create the same real number systems. But Dedekind's approach, it just feels more direct and intuitive when you're thinking about continuity.
Okay.
The idea of a cut, it gets right at this idea of a boundary, and now every possible boundary on the rationals matches up perfectly with a real number.
Right.
It's this very structural way of thinking about completeness that really fits with our intuitions about what it means for something to be continuous. And Dedekind's focus on those ordered field properties right from the start shows a more mature structuralist viewpoint, which, again, is a big deal philosophically.
Okay, so Dedekind creates this rigorous foundation for the real numbers, building them up from the rationales using these set theoretic ideas, especially the idea of infinite sets. And this leads to this huge philosophical question. What's the foundation for all of this? If analysis is now grounded in arithmetic, what about arithmetic itself? Where do the rational numbers come from? Or even the natural numbers, the ones we count with? That brings us to his 1888 work, The Nature and Meaning of Numbers.
Exactly. Having shown how to build the reals from the rationals, Dedekind then looks at the discrete realm. He's asking, what's the essential nature of these building blocks? How should we, as philosophers of mathematics, understand the rationals and the set theory used to construct them? And ultimately, how should we understand the most basic numbers of all, the natural numbers?
And it seems he had some ideas about how to build integers from natural numbers and then rationals from integers, all using set theory, even though he didn't fully publish those ideas at the time.
That's right. In his unpublished papers, his Naklas, he sketches out these constructions that are pretty familiar to us now.
Right.
He imagined defining integers as sets of pairs of natural numbers. Philosophically, this means thinking of an integer as the difference between two natural numbers.
Okay.
And then he sketched out defining rational numbers as sets of pairs of integers representing a ratio. It seems like he saw these constructions as pretty standard logical moves, not as some big philosophical hurdle.
And this contrasts with someone like Kronecker, who famously said that natural numbers are given by God. Where did Dedekind stand on this?
Dedekind, along with Frege, they were on a totally different mission. They wanted to ground arithmetic, and especially the natural numbers, not in divine inspiration or human intuition, but in the realm of logic. That was the whole point of the nature and meaning of numbers. They wanted to see if the basic building blocks of math could be built from something even more fundamental and universal, logic.
So what did Dedekind consider to be the core ideas of logic, the starting points from which math could be built?
For him, it was object. Sometimes he said thing. The German word is Ding, then set or system in German, and lastly, function or mapping, a Bildung.
Okay.
He believed these were so basic to how we think, so universally useful, that they couldn't be reduced to anything more fundamental.
Yeah.
They applied everywhere, not just in math, so he saw them as logical.
Okay.
Now, whether we should call Dedekind a full-blown logicist like Frege is still debated. His idea of logic was quite broad, maybe more like an early form of set theory.
So using these tools, objects, sets, and functions, how did he try to construct the natural numbers? I know he tried to prove that infinite sets exist. That seems like a crucial first step philosophically.
Yeah, super crucial. He didn't want to just assume infinity exists. He wanted to prove it logically, using those basic notions. So he considered the totality of all things that can be objects of my thought.
Okay.
And he argued that this collection has to be infinite. His reasoning was based on this self-referential idea. Even if you take all the thoughts you've ever had, you can always have a new thought, the thought of that collection of past thoughts.
Okay.
This creates a one-to-one mapping from your set of thoughts to a subset of itself, showing it's infinite.
That's a really cool idea. And this leads him to his definition of infinity, which has all sorts of philosophical implications.
Absolutely. Dedekind said a set is infinite. We call it Dedekind infinite now if you can match it one-to-one with a subset of itself.
Okay.
And it's finite if you can't. It's an elegant definition, especially from a philosophical point of view. It doesn't rely on any intuition about something never-ending or the process of counting.
Yeah.
It's all about structure and whether a set can include itself in a certain way.
Okay, so we have this general idea of infinity. How does he get from that to the specific case of the natural numbers? This is where his concept of a simple infinity comes in. How can we understand that philosophically?
So to connect the general with the specific, he introduces simple infinity. It's like the most basic structure that embodies the essence of counting. Formally, it's a set, call it n, that's part of some larger set S.
Okay.
There's a special element, one perp in n, and a function, f, that maps S to itself. And they have to follow 4 rules.
Okay.
First, f has to map n into itself. So if you start with a number in n, applying f gives you another number in n.
Okay.
Second, n has to be the smallest set that contains 1 per and is closed under f. Like you start with 1, keep applying f, and you generate all of n, nothing more.
Got it.
Third, 1 can't be the result of applying f to anything in n. It's like the starting point.
Okay.
And fourth, f has to be 1-to-1. Each number in n gets a unique successor.
Those sound a lot like the axioms we use for natural numbers today. Is this basically an early version of the Peano axioms?
Exactly. They're basically the same thing, just worded a bit differently. In fact, when Peano published his version in 1889, he gave Dedekind full credit.
Okay.
So, to be historically accurate and give credit where it's due, we should really call them the Dedekind Peano axioms.
So Dedekind has laid out what it means to be a simple infinity through these axioms. What's the next step in connecting this to the natural numbers as we know them?
He proves that every infinite set, in his sense of the word, has to have at least one subset that's a simple infinity.
Okay.
And then, and this is really important philosophically, he shows that any two simple infinities are isomorphic.
Okay.
This means they have the exact same structure. You can perfectly match up their elements, the one and the successor function, everything.
Okay.
So philosophically, this means that even if the elements themselves are different, they behave the same way arithmetically.
And that fact that they're all isomorphic is a big deal, right? It suggests that the truths of arithmetic don't depend on the specific objects, but on this abstract pattern.
Precisely. This shows the Dedekind piano axioms are categorical. They perfectly capture the structure of the natural numbers. Any system that follows them will behave the same way.
Okay.
Dedekind said, any truth about one simple infinity translates perfectly to any other. This is like semantic completeness. The axioms capture all the essential truths about the natural numbers.
So we have this abstract structure defined by the axioms, and we know any system that fits this structure is arithmetically the same.
Yeah.
How does Dedekind then get to the natural numbers, the ones we use for counting? What's the philosophical move here?
This is where he talks about creation again, but in a more abstract sense. He says, take any specific simple infinity you've constructed. Now imagine a new set of objects that correspond exactly to the elements of that simple infinity, but they're defined only by their position and relationships within that structure.
Okay.
This new simple infinity, stripped of any extra stuff, that's what he calls the natural numbers. The key here is that these new objects are defined purely by the arithmetic truths, the structural properties that are the same across all simple infinities. Their identity comes entirely from their relationships, unlike the elements of a specific simple infinity, which might have other properties.
He even uses the word abstraction for this, which really highlights the focus on the essential structural features, leaving out any unnecessary details.
Right. If we interpret Dedekind this way, he's very close to a kind of non-eliminative structuralism. This means that the natural numbers are real things, but their essence is totally captured by their role in this abstract Dedekind piano structure.
Okay.
But it's important to note that there are other interpretations of this abstraction step. Some scholars see it differently.
Now, Dedekind saw natural numbers primarily as ordinal numbers, like first, second, third, showing position in a sequence. How does he connect this to their use as cardinal numbers, answering how many are in a set?
He explains that we can get the cardinal use by using those ordered sequences of numbers as tallies, like 1, 2, 3, up to some number n. For any set, we can see if we can match its elements one-to-one with one of these sequences.
Okay.
If we can, the size of that set, its cardinality, is that number n.
Right.
He also shows that a set is finite, meaning you can't map it to a subset of itself, if and only if you can match it up with one of these number sequences.
Okay.
This connects the ordinal and cardinal ideas really nicely.
And on top of all this, he justifies two super important tools in math: proof by mathematical induction and definition by recursion, right?
Absolutely. Based on his theory of chains, those are subsets closed under the successor function. And the properties of simple infinities, he gives a solid logical foundation for both of these.
Okay.
He justifies why mathematical induction works. That's where you prove something for all natural numbers by proving a base case and then an inductive step. And he justifies definitions by recursion, where you define something by saying what is at the beginning and then how to get the next value from the previous ones. These justifications were key for making these common math practices logically sound.
Now, it's clear that both of these works, continuity and irrational numbers and the nature and meaning of numbers, they really rely on set theory. It seems Dedekind was a pioneer in embracing the idea of the actual infinite.
Absolutely. In continuity, he treats the entire set of rational numbers as a complete infinite thing, and then he looks at the infinite set of all possible cuts on those numbers.
Right.
These infinite sets are what he uses to build the real numbers.
Right.
And in his work on arithmetic, he starts by assuming there's an infinite set of natural numbers, and then builds the integers and rationals from there. This willingness to work directly with actual infinity was pretty bold for the time.
Yeah.
Many mathematicians, like Kronecker, they were really skeptical of the actual infinite. They preferred a more constructive approach.
Okay.
It's even said that Dedekind's view on infinity would have clashed with his own teacher, the great Gauss, who was very cautious about infinity.
Right.
Gauss saw it more as a way of speaking, not as a real mathematical object.
And the nature and meaning of numbers really pushes this shift forward by making those set theoretic methods more explicit and by reflecting philosophically on how they're used.
Exactly. In this later work, Dedekind doesn't just use sets. He explicitly says that sets, along with objects and functions, are the basic building blocks of logic itself. He emphasizes that sets are all about their members, what we call extensionality.
Yeah.
A set is defined by what's in it, regardless of how you describe it. This was a huge step towards modern set theory and impacts how we think about mathematical identity.
Yeah.
He was also one of the first to seriously work with sets that don't just contain numbers and to promote the super general idea of a function as any mapping between sets, not just ones defined by formulas or pictures.
Right.
This built on the work of his teacher, Dedekind.
But these ideas, this general notion of sets and functions and accepting the actual infinite, they weren't without criticism, were they?
No, definitely not. Those mathematicians who preferred finitism and constructivism, especially Kronecker, they really attacked these abstract ideas. Dedekind defended his approach by pointing out how useful it was for solving existing problems in math and opening up whole new areas.
Right.
But even Dedekind later realized there was a problem with his initial understanding of sets. He had implicitly accepted this very general comprehension principle, the idea that any collection of things that fit some description is a set.
And this led to those famous set theoretic paradoxes, like Russell's paradox.
Exactly. Through letters with Georg Cantor in the late 1890s, Dedekind became aware of these paradoxes lurking within set theory, like Russell's paradox about the set of all sets that don't contain themselves.
Right.
This really shook Dedekind, even made him question the rationality of human thought for a bit. He eventually came back to his belief in his approach, but didn't solve these paradoxes himself.
So even though his initial understanding of sets had problems, many of his other contributions to set theory were incredibly important and have lasted.
Absolutely. Even though his initial set theory wasn't perfect, so much of his work is fundamental to modern math and philosophy. His analysis of continuity with Dedekind cuts, his definition of infinite sets, those axioms for natural numbers and the proof that they uniquely define the natural numbers, his view of natural numbers as fundamentally ordinal, his explanations for induction and recursion, his insistence on this general idea of sets and functions, and his acceptance of the actual infinite. All these are core parts of modern set theory, model theory, and recursion theory.
Wow.
Zermelo, a key figure in making set theory rigorous, he even said that Cantor and Dedekind were the true creators of modern set theory, recognizing how revolutionary their contributions were.
And his back and forth with Cantor also led to important results within set theory itself, right?
Definitely. They had this really fruitful exchange of ideas. Dedekind, for example, proved for Cantor that the set of all algebraic numbers, those are the roots of polynomials with integer coefficients, is countable. This influenced Cantor's later discovery that the set of all real numbers is uncountable, which showed a big difference in the size of those two infinite sets. Dedekind also independently proved the Cantor-Bernstein-Schroeder theorem, a key result about the size of sets.
And his influence continued well into the 20th century, shaping the development of mathematical logic and set theory.
Totally. His analysis of induction and recursion was expanded to deal with larger infinities by mathematicians like Zermelo and John von Neumann. This solidified Cantor's theories of transfinite numbers, giving a more rigorous framework for dealing with infinities beyond the countable. Dedekind's impact on set theory and the foundations of math is huge, and it's still shaping our understanding of these areas.
This has been an incredibly illuminating deep dive into Dedekind's work. To wrap up, can you summarize the main takeaways for our listeners, especially those interested in philosophy?
Sure. Dedekind's work has a few profound insights that are relevant to philosophy. First, his construction of the real numbers using Dedekind cuts gave us a powerful and philosophically satisfying way to understand the continuous real numbers in terms of the more discrete, rational numbers, all based on set theory.
Okay.
Second, his construction of the natural numbers using simple infinities and the Dedekind piano axioms was a groundbreaking attempt to ground arithmetic in logic, revealing the essential structure of these fundamental mathematical objects.
Right.
And third, his embrace of the actual infinite and his development of those general ideas of sets and functions were crucial for the development of modern set theory, a field with deep philosophical implications for how we think about infinity, mathematical existence, and the limits of reason.
And you've highlighted how connected his mathematical work is to his foundational and philosophical concerns, emphasizing his structuralist approach.
Exactly. Dedekind wasn't just about discovering mathematical truths, he was about understanding the systems and relationships within math. His focus was on the structure, the order, the operations, the mappings, rather than the individual elements themselves. This structuralist view was present in all his work, from number theory and abstract algebra to analysis and set theory. It shows a deep philosophical commitment to understanding math through its inherent structure.
So, for a philosopher looking at Dedekind's work, what are some of the key questions and implications that come up?
His work raises so many fundamental questions for philosophers of math. It makes us think about the very nature of mathematical objects.
Okay.
Are they things we discover in some abstract world, or are they created through our definitions and systems?
Right.
Dedekind structuralism suggests their essence lies in their roles within these abstract structures.
Okay.
His attempts at logicism push us to think about the relationship between logic and math. Can math be reduced to logic, or are they fundamentally different? His use of abstraction as a tool makes us think about how we grasp abstract mathematical concepts and what mathematical truth really is. And the debates about infinity and the set theoretic paradoxes are still central to discussions between different schools of thought in math, like classicism and constructivism.
It seems that even though there were challenges and complexities that emerged later on, his contributions were truly groundbreaking and still matter a lot for how we understand math and its philosophy.
Definitely. The later discovery of those paradoxes in Gödel's work showed that a simple view of logicism has problems.
Right.
But Dedekind's work and his structuralist approach have massively shaped modern math and are still valuable for anyone thinking about the philosophy of math.
This has been a really insightful deep dive into Richard Dedekind's work, and it leaves us with a final thought, especially for those of you interested in philosophy. Think about how Dedekind created numbers, not based on some inherent essence, but defined entirely by their structural properties and relationships within abstract systems. How does this radical idea connect to broader philosophical questions about abstract objects and mathematical truth? What does it mean for a mathematical object to be defined by its relationships? This is a question that's still driving exploration and debate in the philosophy of math, and we hope you keep thinking about it long after our deep dive ends. Thanks for joining us on the Deep Dive.